Today we will talk about tandem solar cell. Tandem solar cell is basically a kind of solar cell where one solar cell is connected with another solar cell, and then both top and bottom solar cells are used to improve the efficiency of the tandem configuration of these two solar cells. So, before I go through the tandem solar cell, let us just look at what are the solar cells we have discussed so far. So, we have discussed silicon solar cell, various thin film solar cell, CDS, CDT solar cell, CIGS, CDS solar cell, and then we discussed about dye sensitized solar cell, and after that we discussed about quantum dot sensitized solar cell and perovskite solar cell. So, now what we have seen in various solar cells, efficiency of the solar cells differ when you go from one type of solar cell to another solar cell. And the theoretical efficiency which has been given by Shockley-Queisser limit, like 33% of efficiency, it seems to be not possible to achieve in any of these single solar cell configuration. Some semiconductor solar cell like gallium arsenide shows in research level quite high efficiency, close to 30%, but these are only in laboratory scale. When we use large scale, the silicon solar cells seem to be better. Perovskite solar cells appear to be highly efficient solar cell, but there are several limitations and disadvantages of the perovskite solar cell, which we have discussed in the previous class. Dye sensitized solar cell have an advantage that it can be used flexible as a flexible solar cell, but the efficiency of dye sensitized solar cell as well as the quantum dot sensitized solar cell are not reported to be high, or they are not close to the theoretical efficiency whatever is reported. Similarly, thin film solar cell like CDT and CIGS solar cell, they also have lot of promises, but their efficiency is also somewhere 19-20%. So, that means all these solar cell which are used in single solar cell configuration do not satisfy the high efficiency criteria, and unless and until a solar cell is highly efficient, we cannot think about this the power or the which need to be used for different purpose, as well as for domestic use and industrial use and all these things. We need highly efficient solar cell for better power output of the device. So, now the question is where we do stand at this moment. So, let us again go back to this the Shockley-Queisser limit. So, this is what we have seen previously, that the efficiency with band gap when it is calculated, and these are various solar cell in efficiency band gap calculation, and you can see this is silicon solar cell, here is the gallium arsenide solar cell, this is CDT, this is CIGS, here is perovskite. These are the class of dye sensitized organic and quantum dot sensitized solar cell. Okay. So, in all the cases, if we look at the efficiency are less than the theoretical efficiency which is given by Shockley-Queisser limit, which is close to around 33% of efficiency. Now, the question is why the efficiency is less, why in practice that one cannot achieve the efficiency of whatever is given by theory. Of course, we have earlier discussed about this, what are the losses that take place in a solar cell. I will just relook at this. Suppose we consider a solar cell with certain band gap, and then incident photon comes, then there is an issue of thermalization when an electron hole pair is formed, and then if this electron is coming down here, it is not absorbed, however it emits a phonon, and that actually constitute a loss which is known as thermalization loss. And now if I consider the photon which is whose the energy is less than the band gap energy, this photon is lost here due to transmission. So the second loss is transmission loss. Okay. And the photon whose energy is close to this band gap energy basically creates an electron and hole, and this is a photon which is useful for the solar cell. So that means it is not possible to absorb all photons that we require to make an efficient solar cell. So what I mean, suppose there are 1000 photons falling on the solar cell, and then we lose photons which are above band gap, and we also lose the photons which are below band gap, and only we use the photons which are within the band gap, definitely a small fraction of this entire photon or entire spectrum which is falling on the solar cell, and therefore we have this natural limitation, and that is to be addressed in some way. Okay. So one way to address this issue is if we can have a variable band gap, and that we have seen in quantum dot it is possible to have variable band gap. Even in perovskite solar cell also, that there is a possibility that one can have variable band gap. But it is not very easy to make a material with variable band gap or different band gaps. Suppose we consider quantum dot sensitive solar cell, then we should have a large number of quantum dots with of some size, and some other quantum dots with different size, and then we can have different band gaps. That practically is not very easy to fabricate. Okay. So one way to get rid of this problem is that we use a tandem configuration or multi-junction configuration. So what is the meaning of tandem configuration? The meaning of tandem configuration is that we can have two solar cells stacked together, and then both are working together at same time with same radiation. So if you look at the configuration of multi-junction solar cell is such that we can have two solar cell, one at the top and another solar cell at the bottom. Okay. This is called multi-junction solar cell or tandem solar cell. So in multi-junction solar cell, what happens? We take one solar cell which is at the top with band gap Eg, which is large, and another band gap one band gap large and another band gap which is small. Okay. So you can think about this particular configuration. I take a large band gap solar cell at the top and a small band gap solar cell at the bottom. Okay. So, what happened? The large band gap solar cell has an option to absorb certain amount of light or some photons which are having higher energy, and smaller band gap solar cell has the option to absorb light of smaller energy. Okay. So, how can I designate it? Let me take it in this manner. So, I have again a red photon, then a blue photon, okay, and both are falling now on the large solar cell. So, large band gap solar cell is first facing both the photons. So, what will happen? This photon, that is blue photon, it will be absorbed in the large band gap solar cell. Suppose you consider a perovskite solar cell, which is a larger band gap solar cell, and this is the this solar cell can absorb the photon with higher energy. So, blue photon will be absorbed here, and then red photon will pass through it, the large band gap solar cell, okay, because its energy is smaller. So, it will transmit through the large band gap solar cell and it will fall on the smaller band gap solar cell, and this red photon will be absorbed now. So, what I have seen in the previous case, that 50% of photons are lost because it is only single junction or single solar cell device. Okay, either you absorb the red photons or you absorb the blue photons. You do not have choice of absorbing both. So, now in this tandem configuration, you make a choice that 50%, that is say blue photons, are now absorbed in the larger band gap solar cell and the red photons are now absorbed in the smaller band gap solar cell. Okay. So, let us see that when I consider this problem in the perspective of solar spectrum. So, let me again look back to the solar spectrum. So, this is the solar spectrum which we have discussed before. So, you can see the along x axis the wavelength is plotted and along y axis irradiance is plotted. So, you can see typically this small blue line which is here, it is only 7% of the solar spectrum, and then there is a broad green line, green band here, whose irradiance is almost 53%. So, large amount of solar photons fall in this particular green band, whose band gap is around say 3.2 electron volt. Now, you come to smaller band gap or larger wavelength regime, then you have all the red photons here. Okay. So, red photons irradiance is slightly less than the green photons, and then it is around 34%, and you cover a band gap of about 1.6 electron volt. If you go further, then you have less irradiance. So, you have pink photons now, which are having 6% irradiance, and then the band gap is falling, which is coming in the range of silicon solar cell. So, if this is the solar cell spectrum which is falling on the material, and then we are looking at say what is happening in the material. So, now if I plot it band gap and then absorption. Okay. So, I can have absorption here, I can have absorption here. I just make two bands out of this, all these bands of photon, I make two bands. So, one band is, I call it red band, and another band is blue band. So, what is the meaning of red band and blue band? Red band and blue band are that the red band are basically the energy bands which are responsible for absorbing photons of lower energy, okay, or the red photons. And then blue band is basically the energy bands of the material which are being used, which can absorb the higher energy photon. Okay. So that means if I just try to compare the solar spectrum and this energy band here and the absorption here with respect to energy band, that means I can have now choice to absorb both red band photons as well as blue band photon, and this gives a higher efficiency when I have a multi-junction configuration, and this is the idea of multi-junction configuration. Okay. So this is a solar cell where this is suppose the first solar cell 1 with Eg large, and this is solar cell 2 with Eg small. Okay. So I just make some ideal case. Suppose this small Eg solar cell have the capability to absorb the band of the red photons, and large band gap solar cell have the capability to absorb the blue photon or band of blue photon. But the advantage is that now both red and blue photons are absorbed in this multi-junction configuration. Okay. So let us see how one can make this configuration. What are the types of configuration here? So if I just draw the tandem configurations, there are two types of tandem configuration which people talk about. One is two terminal configuration. In two terminal configuration, we have solar cell 1 and we have solar cell 2. This is called 2T configuration. So in 2T configuration, both the solar cells are basically integrated. Okay, they are stacked over one another. All right. So if I have a connection here and if I have a connection here, these are the connections in the top cell and these are the connections in the bottom cell. Then I have VOC1 from the top cell or the first cell and VOC2 from the bottom cell. Okay. So that gives me total VOC of the solar cell in 2T configuration. So the advantage of this 2T configuration is that I have one solar cell which is at the top, that is larger solar cell. Let us take this solar cell as perovskite solar cell, and at the bottom, which is smaller band gap solar cell, let us consider this as silicon solar cell, and they are sort of integrated here. That is this is the interface of these two solar cell. Okay. This is the interface region. So you can stack over each other and that you can integrate it. So this is the advantage. But the disadvantage is that as they are integrated, there is some sort of mismatch, because we know that when one material is grown on another material, there is something called lattice mismatch. Okay. So making such interface is basically the interface which we are making, interface, it can create some defects because of the mismatch. If there are defects in the solar cell, we have studied that the defect in the solar cell, basically it reduces the current. Okay. So the current matching is a very important factor here because two solar cells are integrated. So initially people have started with 2T configuration, making one solar cell on top of another solar cell. Later it was realized that one can also make a kind of completely disconnected solar cell. Disconnected in the sense they are not now integrated, they are separated, and I have two connections here, I have two connections here. I have separate connections here also, I have electrical connections, and here also I have electrical connections. Okay. So, this is solar cell 1, again this is say perovskite solar cell, and this is EG large, and this is silicon solar cell, that is EG small. So, idea is same. So, now when you have this particular configuration, again if I just look at what I have discussed before, if I have a red photon and if I have a blue photon, then blue photon will be absorbed here and red photon will come out and red photon will be absorbed here. Okay. Now, I have to integrate them electrically, not in the monolithic integration. Electrically they have to be connected in order to get the output voltage of the solar cell. So, this particular configuration of the solar cell is known as 4T configuration. So, earlier I talked about 2T configuration, that means 2 terminal configuration, and now I talked about 4T configuration or 4 terminal configuration. So, let us now see that when we talk about the efficiency or suppose quantum efficiency, when I have such a configuration with say perovskite solar cell and silicon solar cell, how do they look like? Okay. So, let me just make a schematic of perovskite and silicon solar cell. It is simple, we know that how these solar cells are. So, this is perovskite solar cell, this is the interface solar cell, and then here you remember that we have electron transport layer, and here we have hole transport layer in perovskite solar cell, which we have discussed in the last class, and then I have a small interface here. Then I have silicon solar cell, okay, and this is the back contact. Light falls from this direction. Okay. So, we understand now what will be the mechanism. Mechanism is simple, that the lights with various energetic photons will fall first on perovskite. Okay. This perovskite solar cell will absorb the higher energy photons and the lower energy photon will cross through and it will come to silicon solar cell, and silicon will eventually absorb the lower energy photons. Okay. So, now if I calculate the quantum efficiency of this particular configuration, so you can see how this quantum efficiency look like. So, this is a plot of quantum efficiency where wavelength is plotted along x axis and external quantum efficiency percentage is plotted along y axis. So, you can see, so we start with the lower wavelength regime. Lower wavelength regime means higher energy photons. So, that means this is a top cell, that is perovskite solar cell, and you can see that perovskite solar cell has a quantum efficiency which is close to almost about 85% for a wavelength regime which is smaller. Okay. So, it is, if I look from 300 to say 650 or say close to 800 nanometer, then for a small wavelength regime, it is having a quantum efficiency which is quite high, 85%. And then if we go to smaller wavelength side, the quantum efficiency decreases, if we come to higher wavelength side also, the efficiency decreases. The reason behind this is that if I just forget about the smaller wavelength side, if I just consider the higher wavelength side, then the photons are now all red photons which are going to this side, okay, and the perovskite solar cell does not absorb the red photons, okay. So therefore, now the red photons which are coming to silicon solar cell are started getting absorbed here. So you can see again another band for silicon solar cell which is close to 80% efficiency, quantum efficiency, and for a range of certain larger wavelength, it retains its quantum efficiency close to 80%. Okay, so now the idea is that if I just sort of take a resultant of these two, so I can see that the quantum efficiency can be retained close to 80% or slightly higher than 80% for a large wavelength regime. And this is the entire idea of the multi-junction solar cell or the tandem solar cell. So let us see that what are the typical VOC values that people have reported. So this is actually from the review of what people have done. So you can see the open circuit voltage, how much open circuit voltage one can have. So these are typical configuration. This is with perovskite solar cell with various solar cells. So it is with dye sensitized solar cell, which is typically its VOC value is 0.8, and then if we have a dye sensitized and dye sensitized solar cell both, then we have a typical VOC of 1.4. So only dye sensitivity is 0.8, and if we have DSSC and CIGS solar cell, it is 1.85, and if we have two perovskite solar cell, the red one, which shows very high VOC. So far we have not seen in our discussion that one can also have a VOC about 2.3 3 volt. Okay, so now this is a typical perovskite silicon solar cell which I talked about. This also gives quite high VOC, around 1.74, 75. One can have perovskite CIGS combination, perovskite polymer combination. So typically 1.54 volt VOC. So what we have seen, using this tandem configuration, one can have much higher open circuit voltage value, and we know that we need to optimize the open circuit voltage, because if we have to maximize the efficiency. So if I just consider the single configuration, whether it is DSSC or CIGS, then the open circuit voltage is quite small. And now when we consider all these the multi-junction configuration, open circuit voltage increases, and this is quite large in case of perovskite tandem configuration. That eventually increases the efficiency and overall performance of the solar cell. Okay. So this is what the entire concept behind the multi-junction solar cell, but we have to also look at some drawbacks in the solar cell. Drawbacks in the sense that there are some sort of the losses in the in this type of solar cell. So what are the losses that one can encounter or power losses in case of tandem solar cell? So what could be the sources of losses? One source of loss is the reflection loss. The first loss is reflection loss. Okay, what is a reflection loss? So now if we look at this tandem configuration, there are several layers of material. Okay, so you have, if you have perovskite solar cell at the top, you have an electron transport material, you have hole transport material, and then again when it comes to the conducting side, you have a TCO, and then when you go to the silicon solar cell, you have a metallic contact. So there are several layers now are integrated in one particular solar cell. So what happens when we have several layers? There is having a refractive index mismatch. Okay, so if I consider the refractive index of air from where the light is falling, and then one after another layer through which light is going through or passing through, there is refractive index mismatch, and this refractive index mismatch actually leads to reflection loss, and that has to be taken care of. Okay, so one way of we know that the minimize the reflection loss is to use anti-reflection coating. So there are several anti-reflection coating material which I discussed earlier, but another way to minimize the loss is which also I discussed, that you can make a sort of topography change on the or the microstructural change on the silicon solar cell, or surface you can have some roughness on the silicon solar cell which can trap light. But the problem with this is that when you make a surface roughness of the silicon solar cell which is on the bottom, and on top of that when you try to grow the perovskite solar cell, there will be sort of mismatch because of lattice mismatch, or a kind of the structural mismatch that may actually sort of it will hinder the growth of perovskite solar cell. Okay, so reflection loss is one very important the power loss problem which we have to look at for this type of tandem configuration of solar cell. And another loss is parasitic loss. What is parasitic loss? Parasitic loss is, now again we have different layers which are grown one after another. So if I just consider the perovskite and silicon solar cell, I have now a layer which is, suppose I have also used the anti-reflection coating layer. Okay, I have this electron transport layer, I have hole transport layer, perovskite material, silicon material. They are anyway the main absorbing layers. Okay, but all other layers are there. So what happens when photon falls on that? It will also be absorbed in different layers. Okay, because every the material has some the absorption capability of some range of photon. So these losses we do not want. So these are sort of parasitic losses, because what we want is the main absorption should be in the perovskite solar cell, in the perovskite material, and in case of silicon solar cell, the main absorption should be in silicon. Okay, so all this extra absorption which are for different layers causes parasitic absorption. Okay, and this parasitic absorption can be minimized if we can have a lower charge carrier density. Okay, if we can reduce, because these absorptions are basically happening because interaction of photon with free charge carriers. Okay, so if we reduce the free charge carriers in this material, so we have to choose the materials in such a manner that we have less density of free charge carriers, then all these parasitic losses can be minimized. But remember, that can introduce another loss, that is called electrical loss. What is electrical loss? Electrical loss is a loss where it is typically the Joule loss. So if the charge density of those layers are reduced, okay, that means the current flowing through this through these layers will be reduced. Okay, if the current flowing is reduced, the loss is, in that sense, you will have a minimum loss, thermal loss, but you will have less current flowing through the circuit. Okay, so that actually eventually it adds to the power loss or the reduction in efficiency. Okay, so one is to work with different material and different sorts of configuration of the material, choice of different material, so that one can optimize these three losses, or minimize these three losses so that one can optimize the efficiency as well as power of the tandem solar cell or multi-junction solar cell. Okay, so this is an important thing. Now I just would like to make a summary of all the solar cell which I have discussed so far, and look at that where do we stand now in the efficiency curve. So this is the typical plot here. So you can see over the years people have done, we are somewhere here in this block 2020 to 2040, and this is the research has started from 1940, 1950s, and how people have progressed. So if you see the green one, follow the green curve, this is crystalline silicon. Okay, so how the efficiency of the crystalline silicon increases with respect to time, this can be very nicely presented here. So when we talk about this crystalline silicon solar cell, we are somewhere close to 25% of efficiency, okay, presently, or okay, or in future also, because there is a restriction in terms of its synthesis, in terms of its device fabrication, and in terms of all the losses which we see as far as Shockley cohesion limit. Okay. So now you follow the other curve. Suppose let me look at the perovskite one, that is the green one, which has started relatively recently. Okay, and then you can see the efficiency is slightly better, and one can also reach about 30% of efficiency in perovskite solar cell below the Shockley cohesion limit, but at least 30% of efficiency one can think about. But we have already seen that there are so many drawbacks with perovskite solar cell. The main problem with the issue of perovskite solar cell is its stability. Okay. So now let me see the third one, that is a blue line, which is for multi-junction solar cell. It had started, the concept started little before, but anyway the research has actively started in last 1 or 2 decades. And now if you see the efficiency, it goes very high, and the efficiency one can, you cannot even compete this efficiency of the multi-junction solar cell with the efficiency of all the single solar cell. One can really get an efficiency of 50%. So that means in future we can have a solar cell with 50% efficiency. We can have solar cell on our rooftop which are completely made of multi-junction solar cell. At this moment, the research of multi-junction solar cell as a laboratory scale, the devices are also at the laboratory scale or prototype devices. But if all the problems can be solved and one can have a large integration of the multi-junction solar cell in one particular, the device, then one can have all the solar cell which can be used for generation of power, okay, with high efficiency. And that is what the goal is, and that is where the research of the solar cell is going on presently, and this is where the different research groups are contributing to have high efficiency solar cell using multi-junction configuration or tandem configuration.